तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We have been discussing the velocity overshoot effect and the self-aligned MESFET, that is SAINT it is called. Okay. Now, few things I want to remark what we did, just reviewing what we did last time. We took a look at the energy band diagram, EK diagram, and then said that the velocity field characteristic that you get is due to the transfer of electrons from here to here. And also we said that the energy required to transfer from here to here, from the lower valley to upper valley, depends upon the semiconductor. Okay. It depends upon the semiconductor that you are using. Now, for example, if you take gallium arsenide, okay, the gap between the upper valley and lower valley energy gap is 0.36 electron volts, and this is 1.43. What matters is this gap. Higher this gap between upper valley and lower valley, more is the energy required to transfer electrons, more will be the electric field. So, the transfer of electrons takes place at higher fields. So, that is seen when you compare gallium arsenide and indium phosphide. Indium phosphide band gap is slightly smaller, but this gap is larger. Okay. In fact, I will just skip one of these. So, as a result, you get the electron velocity, steady state velocity versus electric field in this fashion. You can see that the transfer is at 3 kV per centimeter for gallium arsenide, and from that onwards the electrons find themselves in the upper valley. More and more go into the upper valley, where the effective mass is larger. So, its velocity falls. So, when the complete transfer takes place, the velocity is governed by the upper valley. Okay. So, now you can see indium phosphide. This makes a lot of difference for the material, the electrical properties of the two materials. Indium phosphide band gap is 1.43, but the delta E gap between the upper valley and lower valley is 0.53 as compared to 0.36 here. So, the transfer takes place at about 10.5 kilovolts per centimeter, transfer from the lower valley to upper valley. That means higher field. You can call this as the electric field corresponding to peak velocity. So, we refer it as E peak or transition electric field, and that is almost about 3 times the field here. And notice also saturation velocity is not much different, nothing much to boast of. You cannot say gallium arsenide has got very much different saturation velocity than silicon, but the point that we have to notice is there is a wide range of electric field over which the fields are high. Okay. So, now what we saw last time was, in addition to this is a steady state effect. In addition to this, we have the transient effect. The transient effect is like that. Okay. The transient effect, for example, in gallium arsenide, it takes time for the velocity. For example, if you take 1 kV per centimeter, okay, if you take 1 kilovolts per centimeter, let us go back to that curve and see. If you take 1 kV per centimeter in gallium arsenide, it is somewhere here. Okay. for electric fields lower than 3 kV per centimeter, electrons are all in the lower valley. So, they never get transferred to the upper valley. So, they do not go through this, they do not enjoy the benefit of going through that peak field, in the sense that put it in personifying the electrons. So, they will just get accelerated to that steady state value, they remain there. If the electric field is, you subject the electric field, or if you subject electrons suddenly to high electric field. Okay. For example, if you subject to 10 kV per centimeter, you can see that is about the saturation velocity, that is more than 1 into 10 to the power 7 centimeter per second. So, if you take a look at the velocity field characteristics, gallium arsenide, if you subject the electron suddenly to the 1 kV per centimeter, they will saturate out into that. So, you can with time. So, that is what you see here. I will go back and forth between these two slides. 1 kV per centimeter, the energy is not sufficient for transferring the electrons from the lower valley to upper valley. So, they will just increase, and after about a picosecond or 2 picoseconds, they will saturate corresponding to that velocity. If you subject it to 5 kV per centimeter, you can go back to that curve and see 5 kV per centimeter is somewhere here. It is more than the energy required to transfer the electrons from the lower valley to upper valley, but it takes finite time for the electrons to transfer from lower valley to upper valley. Okay. So, during that finite time, before it is scattered to the upper valley, it is all the time in the lower valley. So, as a result, just keep that drawn here. As a result, what you have is, what you have in that situation is, whether it is okay, electrons are all the time here. All the time here during the transient time, and if you subject them to high velocity, high electric field, they accelerate much faster. So, they even cross this energy, and during the transient, when even in networks you know that you subject to sudden pulse, it gets there will be overshoot effects will be there. Similarly, you get the overshoot effect because of that. So, that is why if you subject it to 5 kV, it goes up, then ultimately if you wait long enough, it will saturate onto the velocity, steady state velocity governed by the 5 kV. If you subject it to say higher field, suddenly ultimately it will have to go into this velocity. So, you can just see that higher the field, the rate of change of velocity is, or okay, velocity changes very fast, it gets accelerated fast because of high field, and it reaches even higher velocities, and ultimately goes back to this saturation velocity, and goes quickly to the saturation velocity because it attains that higher energy required quickly, because it rises sharply. You can see the peak here when you apply 10 kV per centimeter occurs much before the peak that occurs here, because it has gone to the higher energy very quickly. So, this is about the I have discussed, I am just summing up what we have discussed last time, because some few things I might have left out. So, I just thought to clarify some of them. Now, the same thing if you plot, as actually as the electron is getting accelerated with time, it also moves forward in space. So, in space also same behavior takes place, only instead of x axis being time, it is velocity into time, that is distance. This gives us a better idea, because after all in the transistor, when we make a device, what we see is how far would it move with that higher velocity. So, that is clear. For example, if you take 10 kV per centimeter, if you subject, okay, then it has velocities in excess of 10 to the power 7 per centimeter, say 10 to the power 7 centimeter per second, okay, over a distance up to about 0.5 microns. So, you can see now if the channel length is less than 0.5 micron, okay, it has not gone into that, the transient phase is not over. As a result, throughout the channel the velocities will be much higher than 10 to the power 7. So, the time required for transit will be very small. So, that is the transit time should be very small, because average velocity is high, and because of that you will get higher GM. This is where the benefit of gallium arsenide is present. Now, let us take a look at indium phosphide. Let us go to indium phosphide first. Again, I just before we go to indium phosphide, I just plotted this for all different fields. Okay. See, for example, 3 kV it saturates. If I go to 15 kV, it saturates at a much lower value. 25 kV it saturates at the saturation velocity. So, what you get here is the saturation velocity, what you get here is the velocity overshoot effect. So, you can see about 0.5 micron channel length if you have, you will get very good benefit for case of gallium arsenide. Let us go to indium phosphide. Indium phosphide also similar transient. The difference is this gap, as I pointed out, this is 0.53 electron volts. The electrons must acquire much more energy. So, the transient effect will be felt longer time, and it will felt on a longer distance. So, you can see now here, supposing you subject electron suddenly to 25 kV per centimeter, almost about up to about 1 micron or at least 0.75 micron, the velocities are higher. Whereas, if you take gallium arsenide, that velocity overshoot effect is over within about 0.5 micron. With gallium arsenide, it is over within about 0.5 micron. Okay? Because it gets transferred much easily compared to indium phosphide. Indium phosphide should acquire much more, it takes more time, because more energy is involved before it gets transferred to the upper valley. So, you get the velocity overshoot effect over a longer distance in the channel. In the sense, you can get benefits with indium phosphide even with slightly longer channels, okay, even when the field is quite high. So, ultimately what we conclude is, if you take gallium arsenide and indium phosphide, the mobility of electrons is high in the case of gallium arsenide. So, low field performance will be much better in the case of gallium arsenide, but when you go to high fields, the performance of indium phosphide you can expect it to be better. But technology has developed much more with gallium arsenide. It is easier to handle gallium arsenide compared to indium phosphide, because you move from silicon to gallium arsenide, indium phosphide, it becomes tougher and tougher to handle the wafer. In fact, silicon is quite hard comparatively. Gallium arsenide, if you hold with a tweezer, you can feel it is more brittle and it is slightly softer. If you go to indium phosphide, if you press the tweezer, you can see the tweezer mark there. It is that bad. Okay. In fact, I was fortunate enough to handle all the 3 types of wafers. So, you can feel you will have to be extra cautious if you want to use tweezers there in indium phosphide. And if you this is the experience that you get with the small cut pieces, but then big wafers, you can see the guy who is holding the indium phosphide wafers will be shivering on his shoes, because that is double or 3 times costlier than that of gallium arsenide. So, that is why indium phosphide you use, but very rarely, but mostly people try to use gallium arsenide. Okay. Now, here also you can see that if I use 10 kV per centimeter, the field 10 kV per centimeter, it is always in lower valley in indium phosphide, because let us go back and see the steady state characteristics. Just remember this, 10 kV per centimeter, that is the peak. Till that peak is there, we have analyzed and seen that the electrons are always in the lower valley. So, if you apply a field suddenly equal to 10 kV per centimeter in the case of indium phosphide, it is never going to go to the upper valley. So, it will go on increasing and it will go to that. It does not experience that transient so much. Okay. So, that is why you see that particular effect there. Now, one thing I just was avoiding all the time is discussing the transient effect in silicon. So, when you say because of the difference in the momentum, because as the velocity increases, energy increases and the momentum also will change, the electrons get transferred to the from the lower valley to upper valley in the case of gallium arsenide and indium phosphide, and as a result you get this velocity overshoot effect because of the time difference between the relaxation time of energy and momentum, because momentum difference is so large there from one valley to other valley. So, silicon people started asking question, don't you see similar effect in silicon? Yes, you will see that. It will not be a transfer from lower valley to upper valley, it is the difference in the relaxation time between the energy and momentum. Okay. It takes a different time to entire thing to stabilize. So, because of that, even in silicon you will see some amount of transient, that is what I projected here. But please note the time frames and also the distances. You do not have to deal with so much of difference in the momentum in silicon. Okay. Here you have to deal with lot of momentum difference. If you talk of silicon, then what you do is, what you have is, you may have a large gap there and you have the small gap here. This is the conduction band edge. Okay. This is the valence band edge. Now, the electrons, they do not get transferred all onto that, everything happens within that, because this gap is quite a bit. So, here as the electrons acquire the velocity, they also have to move into that position. It has to ultimately, this is a steady state curve. During the velocity energy acquired, it will acquire energy in certain time, but it takes a time for that to relax into this momentum, steady state momentum. So, to put it in the language of physics, the relaxation time between the energy and momentum is slightly different. Because of that, you do see slight overshoot and coming back to that point. It may overshoot that, then come back to this point, because of the difference in the relaxation times between energy and momentum. So, you see, but the momentum difference is not so much as in the case of gallium arsenide, etc., not that much, it is only within that curve, EK diagram. So, the transient takes place in a very short time. Okay. So, you can see these dependence of average velocity of the electron, these are simulated curves which we are projecting. Okay. 20 kb per centimeter, there is slight overshoot, close to saturation. 5 kb per centimeter, it is much below the saturation velocity. Saturation velocity is 10 to the power 7. It occurs much beyond 20 kb per centimeter or about 30 kb per centimeter. So, when you subject the electron suddenly to 20 kb per centimeter, you have that slight overshoot, but you see it is not much, it is maybe 1.25 into 10 to the power 7 as compared to 3, 4 times 10 to the power 7 in gallium arsenide and indium phosphide. Okay. Plus the entire transient effect is over in a very short distance. You could have sold silicon with this velocity overshoot effect if this were retained for long time, okay, or longer path distance. So, if you multiply this velocity into time and find the distance over which velocity overshoot effect is present in silicon, that is the curve. Notice here, one thing that you notice here is these are 10 to the power minus 13. So, it is less than a picosecond, the entire thing is about half picosecond, whereas in gallium arsenide it was a picosecond or more, and distances in gallium arsenide were 0.5 micron, indium phosphide 1 micron, up to that you have got velocity overshoot effect. In silicon you can see this is micron, 0.07 micron, it is much less than 0.1 micron. So, if you want to get benefit of this velocity overshoot effect with silicon, what is the channel length that you should talk of? Less than 0.1 micron. Okay. So, when you head towards that channel length, the electrons will experience that, but even that experience is very marginal. It is not much to really be satisfied or really boast of for silicon saying this has so much velocity, it is just 1.25 or so, okay, or 1.75 in that range. It is never 2, okay. 1.5 maybe at 0.5, 1 less than 1.5. So, Okay. But you do get that. So, to be fair for silicon, you get the velocity overshoot effects, but the benefits you will be able to reap only if the channel lengths are very small, of the order of 0.6, 0.5 microns, 0.05 micron, which is tough to achieve. So, now let us go back into what we have been discussing. Ultimately, we said if you have to have the velocity overshoot effects experienced, the electrons must be launched cold into the channel itself, which is short. So, if you are talking of a device like this, I do not go through the process again, because we have gone through the whole thing. The key thing here is you must have the source n plus and the drain n plus. You can see here the final device structure is this. The ultimate device structure is you have got the source n plus, which is actually very close to the gate. This is the gate metal. The gap between the gate and the source should be kept as small as possible. Ideally, they should be self aligned exactly, but you can't do that, because there will be short circuit between the gate and the source, gate and the drain. So, this is the gap. We call it as n plus layer and the gate gap, gap between the n plus layer and the gate. And the channel length is this, because when you apply voltage between the drain and the source, that appears across this. Supposing it is 0.2 micron and you apply 1 volt, it is 1 volt by 0.2 micron, that is the average field that is experienced there. Okay. That is 10 to the power 5 by 2. Okay. So, that is 5 into 10 to the power 50 kV per centimeter, that is large. You will have definitely velocity overshoot effects coming up, but keep this gap small, so that the electrons are launched here, they reach the gate where the control is there immediately, then you get all the benefits right through. Supposing the channel length is very long, you do not get that benefit at all. For instance, if I have a channel long channel with a gate here, source, drain, gate. The electrons, if the field is high, the electrons actually will acquire velocity versus distance. If you take these electrons will go through. So, most of the channel length, the velocity is saturation velocity. If subjected to 20 kV, 30 kV, that is the final velocity. This may be high, but it is over before it reaches the gate. Whereas, if this is short, okay, if this length is short, this comes under that. The overshoot effect is seen under the gate itself. That is actually the real channel where you have you can control everything, current flow, etc. Okay. So, you get the benefits if the channel length is shorter. Okay. You get the benefit of velocity overshoot effect. You also will get the benefit of high mobility when the field is low. Okay. That is, as you vary the electric field, as you vary the drain voltage, electric field varies from low value to high value. When the electric field is low, okay, let me just draw that here side by side. To recall, the V d versus I d curve is okay, like that. Now, this slope here is determined by the low field mobility, and this slope is actually the on resistance of the device. Okay. So, you want this to be as steep as possible. From that point of view, you would like to use the device which has got high electron mobility. From that point of view, gallium arsenide scores over indium phosphide because of the high mobility. Gallium nitride, the material that people are talking of, it is poor in that respect. Its mobility is not as high as that of gallium arsenide or indium phosphide, around 2000. People are improving on the quality of the material to get better and better mobility, the gallium nitride. Right now, that is not for gallium nitride, not for high speed devices, it is mainly used for high power devices because of its high band gap, better thermal conductivity, etc. Similarly, silicon carbide. So, this region can be controlled very easily, or it is much better with gallium arsenide. You will see soon how to get even steeper with the high electron mobility transistors. That we will see now in a couple of lectures later. Okay. So, the key thing here is to have this layer closed. One thing, it reduces the resistance that comes between the gate and this gate and the drain, the ohmic contact. That is one thing. The other thing is the velocity overshoot effects are felt very well. Okay. So, the technology involved is a little bit complicated. Now, let us take a look at what are the, how do these devices perform. If you have this implantation, see, notice here this region is obtained by using this as the mask. What is the gap between this gate and this drain is decided by this undercut, and that undercut is controlled by the etching time. You etch this layer from the top, as you start etching, you keep etching longer, the undercut is more. You can adjust to 0.5, 0.3, 0.15 microns very precisely by controlling the etching time. That all we have discussed last time. Now, let us see what will be the effect of this gap between the gate and this n plus layer and the gate. Okay. And Lg is the note here, Lg is the gate length, and this between the dotted lines you have got the gap between the gate and the n plus layer. This is some of the results that people have reported way back 20 years back. Okay. Some papers have appeared in which they have made these things, some of these devices, though the perfections came much later. Some of the preliminary results they were reported there. Okay. Here what they are talking of is channel width 10 microns, that is the gate width, very small device, 10 microns gate width, gate length is 1 micron, 10 micron by 1 micron. Okay. And you take for a VDS equal to 1 volt, the root IDS versus Vg minus V threshold voltage, if you plot, they get this sort of characteristic, linear root ID, telling you that is square law, which actually what we showed, even when the velocity saturation effects are there, it gives square law. Okay. So, there are two devices which shown here. One is the SAINT, other one is conventional. The difference is only in the n plus implant. Just go back once and see how it will be different. This is the SAINT, self-aligned implantation technology for the transistor, n layer implantation technology. So, if you do not do that implantation, put the ohmic contact here and here, same thing kept, without the n plus layer, it is conventional. All processes keeping same, just avoid that n plus layer, it is conventional. The difference is dramatic. See the two slopes, root ID versus Vg minus V threshold. This is steep, you get much higher values of current for the same voltage and you indicating you that this factor beta is higher in the case of SAINT. It is in fact this is 1.95 millisiemens per volt, millisiemens milliampere per volt. So, milliampere per volt 1.95 for SAINT, and for this it is about 0.56 millisiemens. Ratio of about 3.4, ratio between this transconductance will be about 3.4, tremendous. So, the whole thing is due to two factors. One, because this is actually the effective transconductance that you get, that beta. Okay. So, one reason is, which is everyone is familiar, is the series resistance. See, if you do not have this n plus layer, you get the effect of the thin layer of the channel, which is doped rather lightly, the doping concentration in the channel is decided by other factors like threshold voltage, etc. So, you have the series resistance. The moment series resistance is there, the transconductance is lower, GM0 by 1 plus GM0 into Rs. So, that pulls it down. Number 2, the velocity overshoot effect is present in this case in the channel itself, where if you do not have the N plus layer, that effect is not felt. So, these two things put together, you have got the better performance. Okay. So, this is the one thing that I wanted to point out. Practically it has been demonstrated, and by a factor of about 3 to 4 in that range, that is commendable. Now, this is for one particular channel length and one particular gap that they have provided, about 0.3 or so micron. Let us see the effect of that gap, the gap between the N plus layer and the gate. Okay. I think to keep that focused, maybe I can go to this thing and show you. I will not be going back to this again and again. This is the between this edge and this N plus layer, that is the gap we are talking of, which has been the result of this undercut. Okay. So, now what we are showing is the results that people have achieved with the different gaps. What is the effect of that on the performance of the device? What are the parameters which we talk of as performance? One is the threshold voltage, okay, and other one of course with the transconductance that we have seen, it is already there, good effect. So, this is the threshold voltage effect. On the x axis, you have got the gate length, not channel length, gate length 0.5, 1, 1.5, 0.25. Okay. You can go down right up to 0.25 micron channel length. Then if you measure the threshold voltage by that root ID versus VGS minus V threshold, you can plot, you can get the threshold voltage. That is the circuit engineer's practice to get the threshold voltage. So, when you do that, you get the threshold voltage become more and more negative. Go to shorter channel lengths, keeping the gap as 0.3 microns, keep the gap 0.3 microns, keep the gate length, keep on reducing. In other words, what is happening is that I think I better have the diagram here now. What we do is, because I can point this out better, let me not have the complicated diagram. All that I am telling is N plus layer here, N plus layer there, and of course, the contact. The source, the drain, and you have got the N layer, that is N layer. And you have got the semi insulating gallium arsenide. And the gate is here. That is the gate. That is the LG gate length, and this is the gap. So, what we do is, one set of experiments, we keep this gap at 0.3 and reduce this gate length, which means when you reduce this, if you keep this gap same, that is reduced. For a given drain to source voltage, the fields are higher. Notice these fields in this direction are higher. If I reduce this distance and also cut this down, keeping the gap same, because the voltage applied between the two, the fields are higher. Okay. So, the experiments that they have reported are, one case this is kept at 0.3 microns, one curve, another curve where this is kept at 0.15 microns. So, in the case where it is 0.15 micron, okay, if this gate length is 0.25 micron, if this is 0.25 micron, 0.25 plus 0.15, 0.15. 0.55 micron is the gap. Okay. When Lg is equal to 0.25 micron, you have this total length L will be equal to 0.25 plus 0.3 or 0.25 plus 0.15. So, 0.3 plus 0.25, 0.55. Okay. That is what you get. Point 3 plus 0.25. Whereas in the other case, in 0.3 plus 0.3, 0.6 microns plus 0.85 micron. So, you have got a 0.85 micron in one case, in another case 0.55 micron for the same channel length, gate length. So, the fields are much higher when the L is 0.15 micron. Okay. Now, with that background, I just see this particular diagram. Why? What is happening here? What we see is when the channel length is long for a 0.3 micron channel, for a 1.5 gate length, 1.5 plus 0.6, 0.3 on both sides. So, that is actually 2.1 micron. Okay. There you get threshold voltage of about 0, or slightly more than 0, close to 0. But you keep on reducing the gate length. In other words, you are reducing the channel length itself, you get reduction in the electric field. The threshold voltage shifts negatively. Okay. The effect is worse if you keep the n plus layer gap at 0.15, uncontrollable. See the threshold voltage, what is 0.1, well, close to 0 here. When you reduce this thing to something like 0.25, it is way down there, minus 3 volts, etc., which you cannot tolerate. What could be the reason for this? Okay. There are several reasons. One of the reasons is, if you remember, this layer was implanted through the mask on the top. Okay. The layer was implanted like this. There was something on the top, and this is just I am projecting because it was there when implanted. That is putting dotted line. So, layer was implanted using that mask. So, if this is undercut is 0.3 microns, that is located away from that point. If it is 0.15 micron, that is closer. Now, when you bring this closer and closer, there are two things. One important thing that happens is, it is not as if these implanted atoms, they go just rest vertically like that. Okay. This is a statistical phenomena. When implanted, where it goes and lands, okay, it is a statistical phenomena. When you implant like this here, the atoms which come here, ions which come there, they get neutralized, of course, when they land in the atom, because the electrons come from the back door, from the other contact. So, when it lands, it is neutral after it landed. So, you have a beam current which decides how many atoms are coming. So, the atom can rest here or there. That is called the struggle, statistical phenomena. In the sense, if you take the doping profile here, it goes through a peak, and the peak corresponding to what is known as a projected range. Most of the atoms land there. Similarly, the atom not only has got a right to move in that direction anywhere like that, it also can go like that. It goes here or there. When it comes, it hits with the host atom, and like a billiards ball, hits it, deflected, this also moves. So, both the host and the guest suffer the impact of the thing. The energy transferred is proportional to the masses. Heavier the masses, a heavy fellow collides you, you get knocked more, the lattice atom gets knocked more. Okay. So, the energy transferred is more. Okay. They will come rest early. So, anyway, what I am trying to point out is it will collide. Is one of the motions of this atom, implanted atom, is that of collision, deflection, collision, deflection, till the entire energy is lost. That is the philosophy or theory behind the ion implantation. So, where it lands, okay, when it moves here, whether it lands here or there, depends upon the angle with which it has entered, because after all we are talking at the atomic level. So, when it comes and hits it, okay, if I have the two, one atom lying here, other one coming and hitting directly, then the way it scatters is different. If it comes at an angle, it will get scattered in a different way. So, you will have struggle in this direction and also in that direction. That will be at least 1/3 or 1/5 of the distance which moves, it can be distributed. So, you will have a peak distribution like this. When the atom number of hundreds of atoms come, it can be distributed like this, it can be distributed like that also. So, what I am trying to point out is an atom which comes up here, we have drawn it nicely on the board, saying that this is where the n plus layer is, but actually it comes, it enters into the channel, it enters here. How much it enters? It will enter even the channel. If you bring this closer and closer, if you reduce the gap, it will enter into the channel also. If it enters both this side and this side, if it enters into the channel, what is the result? Dopants are more, the dopants are more, threshold voltage becomes more and more negative. The average dopant concentration becomes more because of lateral struggle, because of the atoms which are implanted very close to the channel get into the channel. So, that is one of the main reasons why the threshold voltage becomes more negative. So, as a result, the advice that people give is, do not bring it that close, use SAINT, it no longer will be a SAINT, okay. It will give you trouble if you place it too close. Okay. So, this gap generally recommended about 0.3 microns is okay. For those energies, about 0.3 micron is all right. Less than that, you will have threshold voltage shifts when you want to have shorter channel lengths. Okay. So, that sort of effects the company. So, that is one thing, but now you can see, you can explain the shift negatively, you can explain by this, because between this curve and this curve, okay, the only difference is the gap. But why should it shoot up here so much? Why should it shoot up here so much when you go to very shorter and shorter gate lengths? That cannot, this should have moved parallel to that almost, but it is shooting up like this beyond that point. Up to this point it is okay, but beyond that point it is too large a change. You have to get into the little bit of physics of this. The physics of this is the field in this direction. See, we are talking of the voltages which are actually 1 volt or 2 volts here, but then 1 volt divided by 1 micron, 1 volt divided by 0.55 micron, high field. Okay. You have got fields in this direction which are high. Now, let us see what happens. In fact, the threshold voltage is measured by using that ID versus VGS at one particular field voltage. So, now let us see what happens. Let me just draw this diagram bit amplified, okay, here. Suppose I have a channel like this, I have a channel like this, that is n layer, I am just magnifying that, this is n layer, okay, and I have the contact far away corresponding to that, that is the contact. Physically it is not ohmic, but not the metal, but electrically that is the contact. when I apply voltage between these two, and this is the VDS, I am showing only the layer. What is threshold voltage? Threshold voltage is the voltage that you must apply to the gate to close the channel at the source end. If this voltage VDS is not there, okay, we saw reducing this affect the pinch off voltage and the threshold voltage. That is one effect that you see there. Okay. So, you get a thing like this, that way you get, and when you reduce the channel length, the gate length, you get these two merging together, the pinch off voltage changes, threshold voltage becomes negative, that we also saw. Threshold becomes more, pinch off voltage becomes more, as a result you have got more and more threshold voltage. That is seen. That effect should have been same in the case of when it is 0.15 micron or 0.3 micron, that curvature effect. But something more happens. The way you measure the threshold voltage, in fact, you are seeing the threshold voltage with the VDS applied. That is what important for you. When you apply VDS, when can you shut off this device? So, what happens is, this is like this, provided all the field lines are vertical or even cylindrical, whatever it is coming like that. But when I have the field like this, which is not any more negligible, if that is larger, what happens? How will the depletion layer be? This is a very interesting thing. In fact, one can simulate and see, and the 2D effects are there. No, let us put a different diagram. This is E x E less than E y, where E y is in the direction, that is the E y. Okay. In this case, actually it will be like this, because plus here, plus charges here and minus charge there, n channel depleted. Now, if E x is comparable to E y, it will not just go down like that, even when the channel length is long. Okay. It will go like this. If this gap is reduced, if I keep it same, okay, for the same gap, I bring it down here. I must reduce it to the same device. All that we did is put the contact here and VDS here. Now, what will happen will be, let me just draw it bit less actually, so that it's what will happen will be, because this field is large compared to this particular field, the depletion layer will not just come down vertically. Even if it is one dimensional, even if it is cylindrical, it will not come like that. The whole thing will get dragged down to the other side. So, what will happen will be, I am going through the whole thing in a qualitative way, because there is no other choice for me other than use some other results. So, this will actually go down, and this is like this. So, instead of being like this, okay, it becomes shifted like this. It does not close here. See, what idea is like this. I have one field line like this, then I will have certain depletion layer width. But if the field line is dragged like this, the depletion layer width will be smaller. Okay. So, instead of coming all the way down, because the field lines are in that direction, pushed in that direction, okay, because of the combined effect of the two, you get whole thing dragged like that. So, result is the depletion layer width, it takes more voltage to close the depletion layer width. You must have higher fields in the direction, so that it becomes close, it is able to close. It is, see, one of the electric fields or volt fields is pushing it down like this, other one is pushing it in different direction in the 2 dimension. So, as a result, you have got, you require larger field in this direction to close the channel. That is why, when the field in the x direction is larger, in situations where the field in the x direction is larger, you require larger field in the vertical direction. That means larger voltage has to close down. That means larger is the threshold voltage negative. See, if this field is larger, if this voltage is larger negatively in that direction. So, what is the difference between the two cases? Here the channel length is long for a given voltage, there is certain field in the direction. Here the channel length is small for same gate length. Channel length is long, so the fields are larger here. So, two dimensional effect comes much more here compared to that. So, the entire depletion layer gets dragged down in one direction. So, it takes more voltage here to close down the channel. That means threshold voltage is larger negatively. Okay. The difference is gap here is more, gap here is less. The gap is less, fields are more in the along the channel. So, you can see the impact of that you see more and more as you go into shorter and shorter gate lengths, because when you go down here the gate length and gap becomes more and more comparable. So, channel length is shorter and shorter. So, you get the two dimensional effect much more here. So, in short channel devices there are two things one has to worry about. One is the curvature effect itself increases threshold voltage. Okay. Second one is the two dimensional effect of the electric field also increases threshold voltage. What is the way you can overcome this? I want to reduce the channel length because I want to get the velocity overshoot effect, etc. better and better, but you land up in problem because you have this two dimensional effect coming up. How do you cut down that? The answer is what you have discussed already. How did you cut down? How can you cut down? I will remove this. We said if I have a long channel, even when the drain voltage is not applied, you will get it like this, the depletion layer. But if you make the channel short, you have seen that for same thickness it will be like that. This threshold will be larger than that we have seen. Okay. How do we avoid that problem? Make the thickness smaller, so that the depletion layer width is small compared to that. Okay. So, this curvature you have a plane parallel portion there. So, you reduce the channel length, channel thickness, okay, and it must be accompanied by the increase in doping. Now, the two dimensional effect, how do you produce? This you are able to do because you reduce it so that there is a flat portion. Flat portion decides your threshold voltage, but in the thing that we are discussing, the only way for you is to ensure that the field in the vertical direction is still large compared to field in the, see the whole thing shift in the depletion layer towards the drain, okay, distortion in the electric field and the depletion layer edge has come about because of that field becoming comparable to the vertical field. Now, if you want to reduce that lateral field, you can't do that. You have particularly reduce the channel, it becomes higher and higher, but make that small compared to this vertical field. How do you do? Increase the vertical field. How can you increase the vertical field? Reduce the thickness and increase the doping. Increase the doping, vertical field is more. For a given thickness, the doping is more, you have got automatically increase in the vertical field. So, that way it is just like saying I want to reduce the length of one line, you draw a longer line near that. So, increase the field in the vertical direction by increasing the doping. So, completely what we are telling now is you get better performance, you can have the benefit of better performance by increasing the doping in the channel. Increase the doping in the channel and also reduce the thickness. You can't keep on reducing thickness, but you can increase the doping at least 10 to the 17, 5 times 10 to the 17, but you can't go beyond that. What happens? If I go beyond the doping 10 to the 5 times 10 to the 17 or 10 to the 18 maximum maybe, this will become ohmic. It will no longer be acting as rectifying contact. There is upper limit to the doping concentration that you can go. More than that, you go to higher and higher doping concentrations, there is one parameter for which you recommended gallium arsenide that deteriorates. What is that parameter? Mobility. Mobility keeps on falling. So, your on state effects get affected, and also the velocity overshoot effect that you get, that effect also goes down, because rate at which it rises, if the mobility, if the doping is increased, the slope reduces. So, the velocity field characteristic goes bit slower. As a result, you do not get the velocity overshoot effects as much as you want. So, from this point of view, you will have to look into other type of devices, where you can still have doping region separated from the region where electrons are present. That we will see maybe in one lecture after this, that is the high electron mobility transistors. I have few things to discuss, which I will continue in my next lecture, that is things like the subthreshold slope. So, I have to discuss what is subthreshold slope and how that affects, and why should we worry about that. That I will discuss next lecture, and then we will go on to high electron mobility transistors. Okay.